router. You might be talking about a router and a router, okay, and so on and so forth. Okay. This cryptographic techniques also works for emails. Okay. And you might be wondering, every time you're trying to contact your bank, let's say you type HTTPS, let's say nz.co.nz, it has to go through the same sort of encryption, decryption. Okay. They need to make sure that your bank account details are secure. Okay. Next, what's the other question? Okay. Earlier I mentioned that Alice could be downloading a public key for Bob. How can she be sure that this is a public key of Bob and not somebody else? Interestingly, there's another, using the same encryption and decryption strategy, we will learn that if Alice trusts an internet certification company, let's call it CA, certification company, and Bob has a public key certified by that particular company, then she can trust that this public key is indeed Bob's public key. We will see the math, how this is done. Okay? And for this course, we will talk about two types of cryptography. You have public key cryptography, and another completely different approach is called symmetric key cryptography. We're going to combine them both for the assignments. Okay? And if you're also wondering what is the math behind this, okay? I did mention that the numbers must be very large numbers. These numbers, okay, even if Bob is making this public key available to everybody, for as long as he keeps this private key, nobody is going to be able to guess what the private keys are. No. Brute force approach will never work in this case. And in this course, we're going to look at the math. Okay? I'm not going to talk about all the details, but to give the class just an overview. It's all based on prime number factoring. Okay? Prime numbers are very difficult to factor. What is a prime number? A number that is only divisible by itself, or 1 and 1. Okay? So here are examples of prime numbers. Okay, 2, 3, 5, 7. And if you're going to start with very large prime numbers, that is at least 1024 bits, then there's no technology that can automatically factor out what are the possible answers. So the attacker cannot possibly just guess. And nowadays, instead of just using 1024 bits, banks started using 2048 bits. How many digits? Oh, I don't know how many digits anymore. So, so complex. And to give you an idea, I showed the class that this is the formula. The message raised to the power of the public key. Let's look at the result of some very simple computations. Okay. I'm going to skip this. I'm going to give the class just an idea, just using simple numbers. Okay. This part here, okay. If m is equal to 17, and let's say e is equal to 29, 17 to the 29, this is a very small number. Look at the result. You cannot possibly represent that in your C++ program using a built-in data type. Okay? What more if this is, containing 309 decimal digits? But there's a way to do these things. Okay? There are mathematical libraries in C++ that you can use, and then no problem. Okay? So you're not going to make use of the basic data structures, but you need to use some specialized ones. And then another thing that is quite interesting, okay, let's say everything will be encrypted and decrypted. Okay, but think about this problem. What if Alice would be sending, let's say, a bank account detail with repeating letters, say AAA? Okay, you might be wondering, oh, that will get the same encoding number. It's going to be encoded using the same number. Okay. Interestingly, we can solve this problem using cipher block chaining. Okay. So in the assignment, we will combine the algorithm I just described, public key cryptography, with cipher block chaining, and let's have a look at the results. So this is, this is quite interesting because for this part, I had to do my own research, and when it worked out, of course, it's fantastic, and I'm going to teach it to the class. Okay. I'm going to show the class a demonstration. If you send AAA, is it going to send repeatedly the same numeric codes? So let's have a look. Okay. And how does it happen? Okay. We will talk about the details later on, but let me run the program. So I've got here some assignment solutions. And to make things easier, because I'm running a client and a server, I've got here a batch file. So I've got the client and a server. Okay. This is the server here. Let me put it on the left. And I've got the client on the right. So here, they're already connected, okay, using my script. Okay. If I send a message to say, hello, okay, what you can see here, okay, is that the word hello has been transformed into a sequence of numbers. Hello only contains HELLO, 5 numbers, but you can see here that I'm doing a bit of padding. Now it contains seven groups, or 7 groups of numbers. Of course, it doesn't make sense. It's just any number, okay? But I want to show the class, what if I send, let's say, AAA, okay? Because AAA will have the same, if you think about it, same encoding scheme. But look at what happens here, okay? The client sends AAA as the numbers 195, 40. They're not repeating any groups of numbers, okay? And when you look at the server, you can see that the server is able to decrypt. So it is able to decode the received message, original message, from this group of numbers back to AAA. So these things would be very interesting, and we're going to go through the math, and we're going to look at how to efficiently implement them. How do you go about that problem where the number exceeds the range for the basic data types, okay, and so on and so forth. Okay, so I'm going to close this one. If I press period, it's going to close. I'm going to close. Okay, in this course we're going to cover so much more. Okay, even this network security topic alone could be expanded into one whole course. I don't know everything, okay, but I'm going to teach you all the essentials, the foundation. Okay. Another problem is what we call message authentication. How can Bob be sure if the message is indeed coming from Alice? Okay, that's another question. We have, of course, the means to solve this problem. And how can Bob check if the message he just received was not tampered along the way? That's what we call message integrity. So these issues: message integrity, secrecy, message authentication, user authentication, and so on and so forth. We will all solve these problems, and we're going to see how we can implement them in an email scenario, for instance. We still have plenty of time. We're going to finish 11:50, okay? Maybe 11:45. So I'm going to proceed to the next topic, just an introduction. This is just very basic. I've talked about so many things already, so maybe some of the stuff here will be repeated. Okay? So some of the important topics and concepts. Okay? Of course, everybody knows what the internet is. Okay? When we talk about the internet, we're talking about a network of networks. But how do you define a network technically? In this course, we're going to see that a network is defined based on the IP addressing scheme. When you look at the numbers, say 130.123, so on and so forth, looking at the IP address as well as the subnetwork maps, actually, we can actually compute for the subnetwork where the computer belongs. Okay? And the internet being a network of networks is defined using using those principles. So we can connect everything, smartphones, tablets, and so on and so forth. And interestingly, even a toaster that burns, that imprints on your bread what is going to be the weather for today. We're going to look at the internet by examining the components that make up the internet. We're going to look at hardware, software components. Earlier we saw that, okay, to communicate, to have two end systems to communicate, they will be transmitting packets that will be traversing several routers and switches. Okay? So we will look at these network devices, and then we're going to look at the services provided by the internet to these distributed applications. Of course, everybody knows this. Using the internet, we can keep files, we can keep images, okay? Important documents. It allows for global communication, and you can use the internet to build your own virtual supercomputer. Okay? Let's have a look. So the internet is a network of networks. Okay? I mentioned this already. There are different protocols and different layers. The internet is also organized hierarchically the protocols are organized according to the different 5 layers. All the standards are specified by what we call the Internet Engineering Task Force. And every time you're trying to implement an application that adheres to some protocol, we need to look at these RFC. So the technical documents are called RFCs. It's called request for comments. It doesn't sound very high-tech, isn't it? But because when the internet was being developed by the scientists a long time ago, they started requesting for comments that eventually became standardized. We are fully aware of these applications, all these killer applications we've got. Of course, the web, where we can download web pages using the internet, of course. Have e-commerce, social networks, okay? And using the TCP/IP library made available by the operating systems, the internet also provides programming interfaces to applications. Here's an example of how to create a virtual supercomputer. Okay? Let's just have a look at it in a high-level view. Okay? At Berkeley, they have built the virtual supercomputer by allowing people to volunteer their machines, idle times. Okay? So what they're trying to do, okay, their group is called SETI at Home. They're looking for some evidence of extraterrestrial intelligence. So SETI stands for Search for Extraterrestrial Intelligence. What they're doing here is that they're making use of radio telescopes. It's not here. Radio telescopes that are trying to send some, what they describe to be narrow bandwidth radio signals. And if they can detect some evidence of narrow bandwidth radio signals from outer space, then it doesn't naturally occur. So that means it must be extraterrestrial. They didn't succeed yet, of course, but that's what they're trying to do, monitoring the outer space. And in order to allow for better coverage of the different frequencies, they need a lot of computing power. So users can volunteer their machine's computing time. They can volunteer during their machine's idle time. It can be used for doing some computations to try and find those patterns, narrow bandwidth signals. Next, we've been talking about protocols. I think using the demo and the examples I've shown the class, everybody is now, getting acquainted. What is a protocol? Okay. Here's just an analogy. For us humans, we communicate by abiding with the prevailing culture. Okay? If you want to ask somebody the time, you need to try and be polite, greet, let's say hi. Not unless you get a positive response that you're going to ask for some request. Okay? For computer networks, network entities also communicate by following some rules. For us, it's rules of etiquette. For machines, it's a protocol definition. Okay? Just like the FTP server and FTP client. Okay? First, the client will initiate the contact. It's going to request for a TCP connection request. Once a connection has been established, that's the only time it's going to request for, say, get hello.php, and then the file is transferred. So the protocol defines the format, okay, as well as the order of the messages transferred between communicating devices. Okay. And it also defines the actions that take place during the transmission and during the receipt of these messages. All possibilities will have to be taken into account. What if the message gets corrupted? What if the line simply gets disconnected? What if the user cannot be authenticated? Maybe the password is incorrect, or maybe the username is not in the database. There has to be these subtleties will have to be included in the protocol definition. And there are protocols for all the different layers. I mentioned that. Protocols also come with different versions. For instance, when we say RFC 959, that's the very first protocol. But this protocol has been superseded, it has been augmented by other extra protocols. So if you want to implement a server for a specific protocol, maybe you'll be reading maybe 5 RFC documents. And each document will be about 60 pages. In the assignment, we're going to limit. I'm not going to ask you to read an encyclopedia, but we're going to limit, let's say we're going to implement only 5 commands. That's it, 6 commands. So these things look familiar now. Okay, routers for route computations. Okay, network interface cards. Okay, for multiple access control and the actual flow of the bits in the wire. Okay. For end systems, TCP is responsible for making sure that the routers do not congest it, so there's congestion control, flow control, so that the server will not be overwhelmed. Next, the network structure. So basically, this is what we have. Okay. To connect to the internet, you might be residing at home, so we've got a home private network, or maybe you're connecting to the internet by way of an institutional network. But all of them will have to be connected together. And so there's some sort of hierarchy. Okay. At the very top, what we call the upper tier, is where we have the backbone of the internet. The backbone of the internet is implemented by, is monopolized by American companies. Yeah, there's only about a dozen of them, and companies such as AT&T, NTT, Level 3 Communications, okay, among the few that monopolizes this business. Okay, they're responsible for putting the fiber optic links along under the ocean to connect continents and so on and so forth. Then, if we're talking about access networks, this is the network responsible for providing you with direct internet access. So at home, we will look at that as well. Okay. Maybe you're connecting to a DSL or a cable network. Okay. And here at NACI, we're connecting to the internet via what we call the Ethernet local area network. Some things that are not very obvious. Okay. When you write a program, let's say you're writing a client web browser. When you write a program, do you need to write a program that will actually compute for the path from your source computer to the destination server? No. You don't need to do all these computations. What's good about network programming is that using the layered approach, we've got the layered approach. can write a program here. This is where you write a program. Your program will be sending messages. Maybe you want to send a file. You don't want that file to be corrupted. So your application, your distributed application could be tapping into the TCP services by way of the socket library. Okay. Next, to actually transmit the packet across the network, it has to be routed across many intervening routers. So this routing will be invoked by calling the appropriate function. The transport layer will be calling the functions made available by the network layer that are responsible for routing. And to actually traverse the Ethernet, for instance, there will be functions made available by the link layer as well as the physical layer. Okay. So what this slide is telling us is that due to the level of abstraction, a client simply relies on the services provided by the protocols underneath the application layer. Okay. So it's like service oriented. What else we don't know? Okay. We've been referring to a client and a server scenario. Okay. Client, FTP client, FTP server. A client is the one that initiates a contact. Okay. And the server will always have to be up and running. But when you think about it, does it always have to be like that? One will always be a server the whole time and another will be a client the whole time. Think about peer-to-peer file sharing. These applications will be a server at one stage and a client. It can be simultaneously be a server and a client at the same time. So it is possible to write an application with many client processes and many server processes. Next, I did mention that every time you're trying to write a program using the socket library, you only have two options. You have TCP or UDP. Okay? I did mention that when transferring a file, okay, FTP client and the server, they have to communicate by TCP. Okay? TCP is what we call a connection-oriented service. It is used if you want to send a file or a message reliably. Okay? On the other hand, a UDP is a connectionless service, offers connectionless service, but it offers fast transmission of messages, but without reliable data transfer. Just to give you, just so that it syncs, you know. Think about this. Let's say you're writing a program, you've got a game network application, and in this game, the user is able to, to run the Gatling gun, with firing hundreds of, bullets per second. When you think about it, do you need a TCP or do you need a UDP? Because if you're writing a program, you need to decide. Okay. Actually, you can combine them. Okay. TCP is, for instance, for logging in, allowing the user to log into a computer a network game. Okay. But when the user is firing bullets at a rate of hundreds of bullets per second or per minute, okay, you can resort to UDP because those bullets will have to hit those targets very quickly. All the other players will have to be notified, oh, I've been hit. Okay? So for those sort of applications, you can use UDP. UDP, unfortunately, does not provide reliable data transfer. That means if you're firing hundreds of bullets per minute, some of them might get lost. The bullet might not, it's like misfiring. Okay? So these things are actually, this is the reality of socket programming. Okay? If you're writing a program that is streaming media, maybe just audio, for instance, it doesn't matter if there's a little bit of jitter in the reception. It's forgivable. But if you're trying to send an email and some of the words got lost, oh, that's not going to happen, right? It's like, okay, see me at this place, and then the place disappears. It has to be completely and reliably transferred. Once we start writing programs, then this is going to become, concrete. Okay, I mentioned this already. I did a bit of demonstrations. We looked at the IP address using ipconfig. Okay. If you want to check if a host is reachable within your network, you can use ping. Okay, and that's that. Okay, let's have a look at that. Okay, let's have a look at that. We have about 12 more minutes. Okay. Let's look a bit more on the networking tools. Okay. So we know ipconfig. Okay. ipconfig tells more about your network connection. IP address. Okay. Let me just identify that again. So we've got the IP address, some of the important ones. What is the name of your machine? Okay. What is the name of your machine? To which domain are you connected to? Okay. ASCII.AC.NZ is a domain. That means it tells you about the network. Okay. Then it also tells you, some of the others are operating system specific. Okay. You also have virtual interface. You have this virtual network interface, which is just dummy interfaces. Okay? They are just there so that a physical interface can be shared among many applications. Okay? So here, for instance, because I installed a program called Tucker, it's using this virtual Ethernet. Then what about the subnetwork? Okay, what's that subnet? This subnetwork tells us what is the subnetwork, to which subnetwork your computer belongs to. If you use the IP address, if you take the IP address and perform an OR operation with your subnetwork mask, then you can compute for your subnetwork. These things will become clear later on once we study the IP addressing scheme. And then what else? DHCP server. Okay. Every time you're trying to connect to the internet, let's say you just brought your laptop to Massey, automatically your machine will be looking for this DHCP server that will assign the IP address. Okay. DHCP stands for Dynamic Host Configuration Protocol. Sorry, maybe it's too overwhelming, isn't it? It's too much already. Any questions so far? No problem. Okay, keep on going. Because I could be giving too much information, but without going through all the basics, it's not going to work very well. Okay, what about this ping? Okay, ping. You're trying to connect to a server, and you're not sure if that server is already on. This is what you can do. Simply call ping. Okay, ping, for instance, the FTP server of Massey, ftp.massey.ac.nz. Is it running? So we can see, oh, it's reachable. Okay. So that's another interesting command, ping. Okay. What about netstat? Okay. Within your machine, you can run many distributed applications. But there's a limit. It depends on how many port numbers you can possibly access. Okay. If you're using IP version 4 for this IP address, okay, you're using 32 bits to represent the IP address. But the port number, okay, let's put that port number. The port number helps identify which process from a specific machine are you referring to? Maybe in this machine, maybe you're running, let's say, an FTP server. This FTP server will have a specific port number assigned to it. Okay? This FTP server is using, let's say, port 21. It's pretty fun. And just to drive drive the point, let's say you have your own game, network game. Okay. Your network game is using, let's say, port 12,000. Okay. That port 12,000 uniquely identifies this program in a machine residing with IP address 130.123.245. All the programs will share the same IP address, but they will have different port numbers. Okay. Now you might be asking, okay, how many port numbers are there? Port numbers are defined using 16 bits. Therefore, this is equal to 65535. However, what you're allowed to use is from 1024 and above. That means you can really have lots and lots of programs running in one computer, and you can have a server and a client, and all of them could be up and running. Depends on the speed of your CPU, if it can keep up with the task that you're putting, on the task you're giving it. Okay. Now let me use NetStat, because that's what I want to show. Okay. Within this machine, how many processes are running? Okay. So I can use NetStat, then I can type space -a. Okay. Then it's telling me, okay, in this machine, you've got the following programs. Okay. There are so many TCPs. Okay. There are so many processes, and what you can see the state, they're all listening. Okay. And you can see the the IP address as well as the port number. 0.0.0.0 means any address. Okay. That means you have a server listening at specific ports. Okay. And at the moment it's not connected to anything, it's just waiting for whatever incoming client. Okay. We can also see that some of the port numbers are used already, are already in connection with another application. Okay. This is my local address, IP address. This is a port number connected to this foreign machine, and it's using HTTPS, and you can see that it is established. Okay. Later on, when you write your own program, you can check to see, is it actually running? You can use this for debugging purposes. And what else? You don't know? So we know that ipconfig ping, netstat. And this is just a summary of what we've done so far. See? ipconfig to find out about your network configuration, where do you which network does it belong to, and what about this default gateway? To connect to the internet, you need looking at my drawing, you need a first hop router. Okay? In this drawing, this is the first hop router, for instance. Before your machine can connect to the public internet, it has to go through that first router. And that first hop router is identified by the default gateway. Okay? So using ipconfig, you can also check for the default gateway in your machine. So when looking at the results, okay, you'll find their default gateway. Default gateway. That's the first point of contact to get any messages out to the public internet and also into your machine. Okay. Then we're familiar with NetStat to look at the different processes running in your machine, either TCP or UDP. NSLOOKUP performs name resolution. Okay. Maybe I didn't run that one yet. Then let me do a demo. NSLOOKUP. say you want to find out what is the IP address of google.com, google.co.nz. So the web server. So you can see, okay, google.co.nz, okay, comes with the following addresses, okay, 216.58.203.99 or this IPv6 address. Okay. So NSLookup is used for name resolution. You'll find that this NSLookup contacts a domain name server, and it's also highly complex. It's using a distributed network of servers to perform this host to address translation. Few more minutes just to make use of, you don't want to waste the time. Okay. Here's an example when I run the following programs. NSLookup gives me lots and lots of IP addresses before for google.co.nz. What does it mean? You're talking to a machine named google.co.nz. But of course, Google wants to provide very fast service, so it has replicated servers. Every time you're trying to contact Google, one of them will be responding to you. That's the point. Okay. Then ping allows you to check for reachability of a specific host. Okay. It could be a server, it could be any machine. Okay. Then router. So I've been talking about routers earlier. Routers are responsible for computing a path, okay, from source to destination. And routers are also grouped within what we call autonomous systems. Okay? For instance, here at Massey, if you want to send a message from your machine to one of the machines here at Massey, then there will be a routing protocol involved for computing the path, only within Massey. If you want to compute a path from your machine to, let's say, another server in the US, it has to go through multiple autonomous systems. Okay? So router, the job of a router is simply to receive a packet, compute for the path, and then send it to one of its outgoing links on the way to the destination. And using this network layer devices, okay, a path may be shared to multiple end systems wanting to send packets across that link. Okay, we know this already. At the network edge, we've got the end systems. The network core, mostly we have routers. Okay. Here are just some more examples. You've seen that. Okay. Traceroute, if you want to find out what are the intervening routers between your system and a destination host. Okay. Traceroute will be probing for the names and computing for the round trip times for each and every router in between the two machines. It's going to transmit 3 packets, okay, to probe for the actual round trip time. So along the path to the destination, okay, 3 probes each, and it's going to tabulate all the results and tell you what is the round trip time, the average round trip time. I think we have to stop here, otherwise I think it's too much for the class in 2 hours. Any comments, any questions so far? It's just an overview. Okay? Next meeting we will look at the different access networks. We're not going to write the program immediately, okay? I'm going to give the class, I can let the class view some of the lectures, early on, but I will keep on updating them. Programming will only happen after we've covered at least the FTP, because that's for the first assignment, and then we can start looking at how to use TCP, how to use UDP. Maybe I can rearrange a bit some of the topics so we can have earlier hands-on socket programming experience. Any other questions? Thank you very much, class, for your attention. Have a nice day. Thank you.